We are going to apply the Laplace transform to solve this differential equation with initial value conditions. Right, so to solve this differential equation with Laplace transform, we will have to take the Laplace transform on both sides of the differential equation. Before we do that, we will have to find the Laplace transform of what the derivative of the y prime prime of t is. So in my previous video, we derived this. So the Laplace transform of y prime of t, Laplace transform of y prime of t, this is equal to s multiplied by capital Y of s, which is the Laplace transform of y of t minus the initial condition. The Laplace transform of the second derivative, that is y prime prime of t, this is s squared multiplied by capital Y of s minus s times y of 0 minus y prime of 0. We derived this in my previous video, so we will have to go ahead and now take the Laplace transform on both sides of this differential equation and then apply what we know. Alright, so let's do that. So the Laplace transform on the left hand side, that is y prime prime of t plus y of t, right? And this is equal to the Laplace transform on the right hand side, which is sine of t, like this. So applying the linearity property of the Laplace transform, we are going to have the Laplace transform of y prime prime of t and plus the Laplace transform of y of t, like this, and this is equal to the Laplace transform of sine of t. Alright, so now the Laplace transform of y prime prime of t is what we have here, so I'm just going to replace it. So that is s squared multiplied by capital Y of s, the Laplace transform of y of t, minus s times y of 0 minus y prime of 0. Those are the initial conditions. Plus the Laplace transform of y of t, that is going to be capital Y of s. And this is equal to the Laplace transform of sine of t, that is going to be 1 all over s squared plus 1 squared, and 1 squared is 1. Now let's replace our initial conditions in this equation on the left hand side. So y s squared times capital Y of s minus y of 0 is 1, so that is going to be s times 1, which is s, minus y prime of 0 is 0, so I'm not going to write that, I'm just going to add this y of s, so plus capital Y of s, and this is equal to 1 over s squared plus 1. Cool. So now the next thing is to take this s across. So this one is going to be s squared times y of s plus y of s, and this is equal to 1 over s squared plus 1 and now plus s, like this. So now let's factorize y of s out, which is the Laplace transform of y of t, and this is going to be left with s squared plus 1, and that is going to be 1 over s squared plus 1 plus s. So now to isolate y of s, we will have to divide both sides by this guy, which is s squared plus 1, and doing that we have capital Y of s to be equal to, dividing both sides by this, the left hand side is going to be left with y of s, and the right hand side is going to be this 1 over s squared plus 1, this is all squared, plus s all over s squared plus 1, like this. So to find the solution to this differential equation, we will have to find y of t. So what will be a function y of t which will satisfy this equation, differential equation? So to find y of t, we will have to take the Laplace inverse on both sides. This is the Laplace transform of y of t, and now if I have it, the Laplace transform of y of t, if I want to get y of t, I will have to take the Laplace inverse of y of t, of capital Y of s. This is what I mean, and doing the same thing to the right hand side, we will have this, the Laplace inverse of 1 over s squared plus 1 all squared plus s all over s squared plus 1, like this. So the Laplace inverse of capital Y of s, this one is going to return our function in the t world, which is y of t, and this is equal to, now applying the linearity property of the Laplace inverse, we have the Laplace inverse of the first one, which is 1 over s squared plus 1 all squared, plus the Laplace inverse of s all over s squared plus 1, like this. Cool. So now we know this, we know the Laplace inverse of s over s squared plus 1. Let me do something here just to remind you. So the Laplace transform of cosine of t, right, this is equal to s over s squared plus 1 squared, which is 1. So in that case, if we are taking the Laplace inverse, right, if we are taking the Laplace inverse of s over s squared plus 1, This one is going to return our function in the t world, which is cosine of t. So this one is just the cosine of t. So let me replace that, and then we deal with the first Laplace inverse. So the Laplace inverse of this guy, the first one, that one we are going to apply the convolution theorem, because we can't use partial fractions to break this one down, plus the Laplace inverse of this one, which we got to be cosine of t. So job done for the second one. This one is easy relatively, but we will have to use the convolution theorem to find the Laplace inverse of that. So convolution theorem, convolution theorem. So we are going to apply the convolution theorem to find the Laplace inverse of this. So now let me switch colors. Let's say to blue. Okay, so now the Laplace inverse of 1 over s squared plus 1 all squared. This one can be broken down into the product of two different functions, and that is this, the Laplace inverse of 1 over s squared plus 1 multiplied by 1 over s squared plus 1. Simple as this, right? So the Laplace inverse of the product of two different functions is going to be the convolution. So this one is going to be the Laplace inverse of the first one, which is 1 over s squared plus 1, like this. But this is going to be convoluted with the Laplace inverse of the second one, which is the same thing, 1 over s squared plus 1, like this. Cool. So now I'm not going to write this one all along. So this one is going to be, so the Laplace inverse of 1 over s squared plus 1. So if the Laplace inverse of s over s squared plus 1 is the cosine of t, the Laplace inverse of 1 over s squared plus 1 is the sine of t. So the first one here is going to be sine of t. So it's going to be sine of t convoluted with sine of t as well. So this one is also the sine of t, the Laplace inverse of that. So this sine of t convoluted with sine of t is not what we want. We will now have to use the definition of the convolution to find the real value of this convolution. So now let me refresh your memory again. So if we have f of t convoluted with g of t, this one is the integral from 0 to t of f of t minus tau. This is multiplied by g of tau and then d tau. This is the definition of the convolution. So here f of t is sine of t and g of t is sine of t. So the two functions here are the same. So now let's see how we can find the sine of t convoluted with sine of t using the definition of the convolution. Cool. So now let's do that. And when we find that, that one is going to be added to cosine of t, and that should be the answer to our differential equation. So good luck with the convolution, and now let's do that. So sine of t convoluted with sine of t, a function convoluted with itself. Applying the definition, that is going to be an integral from 0 to t of f of t minus tau. The first function is sine of t. So this one is going to be sine of t minus tau, like this, multiplied by g of tau. The second function is sine of t, and now that is going to be sine of tau. And we are integrating with respect to tau, that's d tau. Cool. So now let's solve this. So sine of tau convoluted with sine of tau, this is the integral from 0 to t. Now applying the double angle identity, sine of t minus tau, that is going to be sine of t, and then cosine of tau. This is the first one, minus the second one is going to be cosine of tau. Cosine of t, and then sine of tau, like this. And this is multiplied by sine of tau and then d tau. This is sine of t convoluted with sine of t. So sine of t convoluted with sine of t, this is equal to, let's distribute in with sine of tau. So now we have the integral from 0 to t of, this one is going to be sine of t. So let me do this one at once. So this sine of t is a constant in the tau world, because we are integrating with respect to tau. Sine of t is a constant. So I'm going to pull it out of the first integral, sine of t. Then I'm going to have the integral from 0 to t of cosine of tau times sine of tau. That is going to be sine of tau and then cosine of tau. Right. Now the next one, that is d tau. The next one, cosine of t, is going to be a constant in the tau world, so I'm going to pull it out, which is cosine of t. Then the integral from 0 to t of sine of tau times sine of tau, that is going to be sine square of tau, and then d tau. Cool. So now applying the double angle identity again. So permit me to multiply this one by 2 and nullify the effect by dividing the integral by 2 like this. And now this one is equal to what from the double angle identity. So sine of t convoluted with sine of t. This is equal to 1/2 sine of t in front in the first integral. And now this one is the integral from 0 to t of sine of 2 tau. Right, d tau minus this one using the double angle identity again. This one is going to be the integral from 0 to t, and then sine square of tau can be written as 1/2 into 1 minus cosine of 2 tau like this. And now d tau. Cool. So this 1/2 I'm going to pull it out of the integral, this one. So I'm just going to have this divided by 2, so that is like 1/2 times cosine of t. So now we are ready to integrate. So sine of t convoluted with sine of t. This is equal to 1/2 sine of t in front of the first integral. And now integrating sine of 2 tau, that is going to be negative 1/2 cosine of 2 tau. Then the limits of integration from 0 to t. Right, so minus 1/2 cosine of t. And now integrating 1 minus cosine of 2 tau, this is going to be tau minus 1/2 times sine of tau, 2 tau. Beg your pardon. So this one we are done with the integration, the limits of integration from 0 to t as well. Now let's plug in the limits. Sine of tau convoluted with sine of t, the sine of t convoluted with sine of t, this one is equal to 1/2 sine of t. And now this negative, I'm going to bring it out because it's difficult to be handling negatives when you are subtracting. And now we are going to have 1/2 cosine of 2t, that is the upper limit, minus, when you plug in the lower limit, what do you get? That is going to be 1/2, because cosine of 2 times 0 is cosine of 0 and cosine of 0 is 1. So this is what we have for the first one, minus the second one, we have 1/2 cosine of t. And now let's plug in t. So t minus 1/2 times sine of t, sine of 2t, like this. This is the upper limit. The lower limit is going to be 0. 0 for this is 0, and sine of 0 is 0. So there's no need to write the lower limit. We are done. So now let's distribute with 1/2 sine of t. So sine of t convoluted with sine of t, this one is going to be this one multiplied by this one. Let's do that one first, because that one is going to be positive 1/4, and then we have sine of t like this, and this one is going to be negative 1/4. Then we are going to have sine of t and then cosine of 2t like this. Now let's go to this one. That one is going to be minus 1/2 t and then cosine of t, and this one is going to be positive plus 1/4 cosine of t and then sine of 2t like this. Cool. So now let me bring this one and this one together, and now this is what we have. We have sine of t convoluted with sine of t. This one is going to be 1/4 times sine of t minus 1/2 times t times cosine of t. And now let me bring these ones together and factorize 1/4 out. I'm going to write the positive version first, so that is going to be 1/4. And now this is what we have. We are going to have sine of 2t and then cosine of t. And I'll bring this one. 1/4 is factorized out, so it's left with minus sine of t. So let me write minus cosine of 2t minus cosine of 2t and then sine of t like this. Cool. So now from the double angle identity, let me show you here. From the double angle identity, if you have sine of 2t minus t, what do you get? Sine of 2t minus t from double angle identity, this is going to be sine of 2t and then cosine of the other one, which is t, and now minus, we have cosine of 2t and then sine of t. So we see that this one and this one are exactly the same. So instead of this one, I'm just going to replace it with this in my next line. So now let's do that. So sine of t convoluted with sine of t, convoluted with sine of t, this is equal to 1/4 times sine of t minus 1/2 times t times cosine of t like this. and now plus 1 over 4. Instead of this, I'm going to replace it with that, and that is going to be sine of 2t minus t. And sine of 2t minus t is sine of t. So this one is going to be 1 over 4 sine of t plus 1 over 4, that is this guy, sine of t, plus 1 over 2 times t times cosine of t. And this one is equal to 1 over 4 sine of t plus 1 over 4 sine of t, that is 1/2 sine of t minus 1/2 t cosine of t. And this one is sine of t convoluted with sine of t. Right, sine of t convoluted with itself, sine of t, like this. So now we have gotten the second Laplace inverse, which is this guy, 1/2 sine of t minus 1/2 t cosine of t. So what I have to do is to go back up here and now finish up with our solution. So y of t, which is our solution, is this. So that is the Laplace inverse of this one, which we just found, plus cosine of t. And cosine of t was the Laplace inverse of this guy. So y of t, y of t, which is our solution, is the Laplace inverse of 1 all over s squared plus 1 all squared, right, plus cosine of t. Right, this is what we have. And the Laplace inverse of 1 over s squared plus 1 all squared was the convolution of sine of t and sine of t. And that one is gotten to be this. So let me just replace that. So y of t is equal to 1/2 sine of t minus 1/2 t cosine of t plus cosine of t, like this. And this one is the answer to our differential equation. So y of t is going to be 1/2. You can factorize that one out, and now this is left with sine of t here minus t times cosine of t plus cosine of t, like this. Or you can put this one, everything in the parentheses, right? This one is going to be plus 2 times cosine of t, like this. All right, so this one is the answer to this differential equation. So cool. So the first one, you really have to use the convolution theorem, because this one you can easily break this one down using partial fractions. We are going to get the same thing in the end, so we just have to rely on the convolution theorem to solve that. And this one is the correct answer. If you can verify this by differentiating this one once and do it again for the second time, and then plug the results back into the original differential equation, which is this one here, and then we see that the left hand side will be equal to the right hand side. So that is the solution to this beautiful differential equation. If you have any questions, please leave them in the comment section and I'll do my best to respond to all of them. And if you really enjoy this video, subscribe to the channel, and then I'll come your way again with differential equation tutorials. I thank you so much for watching, and then I will see you in the next one. Bye bye.